In this video tutorial, we're going to discuss about synchronous data path for our neuron model. On the previous design, we have designed this neuron core, which was combinational, which means that the output Y of the neuron core relies on the input it receives, which was axon and synapse at that instant, and it stays independent of time. If you remember that on our neuron core, we didn't have time, which was clock. Now, since we're going to introduce clock, so our design will be a synchronous design, and the output does not relies on the current input. It can relies on the previous one. We're going to discuss this when we're going to design our registers. So in order to achieve this design, we're going to have one ring counter and registers for our input value and our output. So we're going to design one register, and then we're going to use it, and then this is going to be a parameterized register, and then we're going to design also a up counter of 4 bits. So the first thing that we're going to design is this the register. So this register, it is going to be a parallel load register with a synchronous reset. This one is a flip-flop, and it can store 1 bit, 0 or 1. So since we want to design a 3-bit register, so the n is going to be 3-bit. So a register it is a group of flip-flops. So when we're going to design a 3-bit, we need a 3 flip-flop to have a register of 3-bit. So for example here, if you want to design a register, we need a 3 flip-flop. So for example, since this is synchronous design, we're going to need a clock. And then the D flip-flop, this is a D flip-flop, and the inputs is D. So for example, we want to register number 4, for example, is 0, 0, 1. So the input is going to be 0, 0, and then 1 here. And then we need a reset. So we're going to reset our value. So we're going to call it ER for reset. So this we're going to connect to all of our flip-flops. And then, so since this is a synchronous design, so for example, if we have a clock here, so this register is going to be operational at the rising edge, clock at the rising edge. Now, for example, if you want to save, for example, this number 4, we need to have a controller. So that means that is a synchronous load. We can have a asynchronous or synchronous. So this is going to be a synchronous load register. So it means that we need to control it with a load when we want to load our value. For example, this is going to be our control, and then we can call it load, and then this is connected to all the flip-flops. So for example here, if you want to save 4, this is going to be active. For example, this first clock here, and then this is a second clock, third clock, and fourth. So if you want to save number 4 here, so for example, if we give our D input 4 in the first clock, 4, and then here we give 5, 6, and 7, and then this is going to be our input D, and then the output, which is Q, is going to represent at the next clock. So you're going to have 4, 5, and 6, and 7 here. But we need a load to control when we want to save our value. For example, if the load here, in this case, the load, it was high for every value, so load is high. But for example, if our load here, it was low and then high, here we'll have our reset value. For example, if our reset value at the first clock it is 0, we're going to have 0 here. Then we're going to have 5, 6, and 7. So let us design this register on the Verilog code.